So this is the beginning of the second hour. And just another reminder that next week will be your first exam. And I have just limited so that you have just chapter 1 and chapter 2. After the exam next week, I will cover chapter 3, which will be part of exam 3. And it's also very important in the context of the cell. So in other words, what does the cell use cellular respiration for, right? And break down glucose completely to generate ATP, for example. Okay, so as a way of reviewing what we just talked about, and keep this in mind, there are some molecules that is considered as nonpolar, some molecule considered as polar, and good example of polar molecule is think of water and glucose. Okay, a polar molecule. And polar molecule like to interact with water, right? So you put sugar in tea, water, sugar would dissolve, right? And it like to interact. Oil, in this case right here, fatty acid, and this is a typical example of a dietary fat known as triglyceride. And triglyceride, you see here, composed of one molecule of glucose uh, and one molecule of glycerol and 3 molecules of fatty acid, right? So in the future, maybe an exam question is like, what is triglyceride composed of? 1 glycerol and 3 fatty acid. And fatty acid, why? Because all of this is fatty, okay, hydrocarbon. This is one functional group right here, C double bond OOH, that's an acid. C double bond OOH, that's an acid. C double bond OH, an acid. And this is considered glycerol. And in nomenclature, molecule that ends in OL is considered as alcohol. And what does that mean? That means it has an OH. That OH is linked to that acid. So alcohols and acid can typically links together. That's an OH. That's an OH was before glycerol and 3 fatty acid. That's triglyceride. An amphipathic molecule, in this case, is phospholipid. I drew for you that here's a phospho group, right? In general, we call this as the phospho head because when we look at the plasma membrane, which is the boundary of the cell, is composed of phospholipid, right? But phospholipid bilayer, so it has 2 layers of this. But in other words, here's a phospho head, which is polar, that often finds on the outside of the cell, and then here's your acid, right, which is nonpolar. By the way, does anybody know what is the difference between this hydrocarbon and this hydrocarbon? What's the difference between this hydrocarbon and this hydrocarbon?
The double covalent bond between carbon.
Yeah. So here's a double covalent bond. And so you guys ever heard of omega-5, omega-7? You ever hear that thing? Omega fat is considered good for you. Omega. Yeah, okay. So you know what the term omega, why is that important? You know, I don't know if you guys are religious, right? They describe Christ as say that, oh, he's the Alpha and the Omega. Yeah, Alpha is the beginning, Omega is the end of the last, right? And so when they say omega-5 or omega-7, that's describe where the locations of the double bond is. So you say 1, 2, 3, 4, 5, 6, 7, 8, 9. This considers omega-9. Okay, this is where the double bond would be. So omega-5, we 1, 2, 3, 4, 5. There's a double bond here, right? 6, 7. That's omega-7 double bond. Now, also structurally, the double bond changes the structure, if you will, from a single carbon, right? So in other words, this is considered linear hydrocarbon, whereas this is a little kink to that, right? There's an angle. And so in fact, saturated fat, you call this is unsaturated because it has still have one double bond in there. So that's unsaturated. Okay, so that's how did you define saturated fat versus unsaturated. So this will be considered unsaturated fat, whereas this is uh, saturated fat. The reason why saturated fat is bad for you right here, because saturated fat composed of these all hydrocarbon like lard, right, which is actually solid, and solid fat is kind of bad because that solid fat could accumulate in the inside of your blood vessel and could lead to clog. um, like think of it as like too much fat in your plumbing, you can clog it up and you could interfere with the blood flow. Unsaturated fat is considered good, like omega-5, omega-7, omega-9 in this case, is good is because there's a kink, and unsaturated fat tends to be like oil, and oil is not fat, right? And that's the reason. All right, let's move on. So the interaction with chemical interaction between this molecule and this is very important. Come from this idea of water, right? So water typically looks something like this, right? An oxygen and a hydrogen, where this is likely positive and this end is likely negative, right? But here's another water molecule, right? And where this is slightly positive and this is slightly negative. But this interactions between this slightly positive and slightly negative is known as hydrogen bonding, right? So here's your third bonding. We saw ionic bonding. It's between cation and anion. Covalent bonding, which is sharing of pairs of electrons. And now this is a third bond. It's called hydrogen bond. Hydrogen bonds are formed between polar molecules. You see here? So here's a molecule. Here's a polar molecule. Here's another polar molecule. And it's hydrogen bonding. It's weak bonding. It's weak between um, um, molecules, but there are many hydrogen bondings all around. This hydrogen bonding is very important because it allows us proteins to fold into three-dimensional structure, right? So proteins are made of amino acid, so it could be three-dimensional structure like this because of hydrogen bonding. DNA is oftentimes is considered as the double helix like this, and its double helix is because there's hydrogen bonding between the bases. Um, AT, we're going to talk about nucleotides, adenosine triphosphate, has two hydrogen bonding with thymidine triphosphate, and guanosine triphosphate has three hydrogen bonding with cytidine triphosphate. Okay, so hydrogen bonding is formed between polar molecule. It's considered as weak individual, but together they're very, very strong. And here it shows you a hydrogen bonding between a sugar molecule, glucose, right, and water. You see here? Here's the slightly positive, here's the slightly negative. So that's why glucose is polar molecule, and it like to interact with water. So both carbon dioxide and water have two polar bonds. However, the dipoles in the layer of the carbon dioxide molecule cancel each other. So in other words, Carbon dioxide, even though it has a carbon, which is considered organic, and it does has unequal shares of pairs of electron, but because there's two of them, they cancel each other. So carbon dioxide and water, it carbon dioxide is considered as nonpolar. Organic versus inorganic, I told you already. Organic is basically a compound that has carbon, with the exceptions of carbon dioxide, and inorganic or other stuff like water, salt, acid, and base. How do you find an acid again? Does anybody tell me what an acid is? Tell me what an acid is. An acid is a molecule that does what?
Gives off a hydrogen atom.
Ion. Yeah, good. That give off a hydrogen ions, right? Which in general we can call that is a proton. Um, so an acid is a molecule that give off a hydrogen ion or a proton. Now, on the other hand, a base is a molecule that accept okay, a hydrogen ion. Okay, so that's the difference between an acid and a base. So, for example, if you think of this one, HCl, hydrochloric acid, you put a water, it dissociate into hydrogen ion and a chloride. Okay, Cl minus. Okay. Likewise, H2SO4, sulfuric acid, very strong acid. Break it down to 2 hydrogen ion and SO4 with 2 minus. A base, let's say OH is a hydroxyl, is the base, right? Now, if there's hydrogen ion in water, like this, together, a base, like, sodium hydroxide, for example, is a base, because you put sodium hydroxide into water, it becomes sodium, like this, and hydroxyl group like this. That's hydroxyl group, which is same as this, interact with water to become water. Okay. So hydroxyl group can interact with the hydrogen ions to form water. Okay. Water, so I'm not going to talk about too much about this water. It's the most abundant molecule in our body, constitute about 60% of the human body. Okay, is made out of water. Two-third, yeah, about 66%. Okay. And water can exist either as a gas, liquid, and solid. We already know that. Do we know what water freezes at? Like outside, there's some water solid, the snow. What's water freezes at?
0 degrees Celsius and 32 degrees Fahrenheit.
Yeah, I'm sorry. Who just? I can't say who is talking. Who just say something?
Luciana.
Okay, good. So I recognize the voice, Luciana now. All right, great. Moving on. Okay, so water plays such an important function in our body, remember, right? It could transport um, molecule like nutrients as part of the blood, um, oxygens, right? Waste. By the way, what organ system that releases hormone into the blood? What organ system is that? Elsie?
Endocrine system.
Good, beautiful, right? And a lot of water uh, is part of the fluid that important for lubrication. Uh, and this is part of the serous membrane that I didn't really get a chance to talk with um, chapter one, um, but involving in lubrication. Uh, of course, water component can cushion the blow. I imagine this could be the same as, Kung Fu Panda. You have all that fat in there. And when, the tiger hit him and his body just swayed with it, uh, absorbing the force, if you will. And of course, excrete waste from the body. Remember, blood also carry heat. Where does the blood go? Uh, Heat will follow. So, in other words, here's another review question for you. Is someone who is developing hypothermia, would you see vasoconstriction to the skin or vasodilation? Anybody? Hypothermia.
Vasoconstriction.
Vasoconstriction, very nice. All right, continue with the water. Water has cohesive molecule. Very important is that uh, in the alveolus, okay, like this, which is basically, um, oh, here's another question for you. What organ system allows you to take in oxygen and release CO2?
Cardiovascular?
No, take in oxygen and get rid of CO2. Transport oxygen and transport
Respiratory.
CO2. Respiratory, yeah. Okay, so here is a an example of these um, uh, we call it the respiratory tract that start from your mouth or your nose. It goes into your pharynx, your larynx, your trachea, your bronchi, and it goes all the way to the end. We call this is the alveolus. Okay, and this is where oxygen. So here's your blood. Okay, and what gas, particular oxygen, would come in, and CO2 will get escaped. Okay. And of course, during the pandemic, if you get a lot of inflammatory reactant to the virus, this whole area will fill with fluid and that will interfere with the gases exchange. So gas cannot enter to oxygenate your blood. People have problem breathing. Their oxygen, saturated oxygen content decrease. Normally, if you're above 90% is good, 60% is bad. But the discussion here is this: there exists a water, okay, in here, and so when this collapse, there's potential that this water surface tension between the membrane, like this, doesn't opens up. Okay, so you ever have two glass plate uh, and trying to separate them in water? They're really hard, right? The way that you want to separate them is that you probably want to use an amphipathic molecule like soap or detergent. Detergents or soap is considered amphipathic because on one end is polar, the other end is non-polar. Okay, and so in our body, to prevent this from happening, what happens is that there's a liquid that these cells make. It's known as a surfactant. Okay, And surfactant is an amphipathic molecule that prevents this water adhesion, like you see here. Okay, attraction between water molecules due to hydrogen bonding. Surface tension is the inward pulling. This is because of this surface tension that you often see. Oh, here is actually called surfactant as well, and causes the moist sacs of the aerosol lungs to collapse. But if you add surfactant, this will prevent it. Okay. Now, surface tension is what really you guys see this is in the lab. So here's a graduated cylinder, right? And the marking here's here's your 10 ml, here's your 20 ml. And you want to measure 20 ml, you want the bottom meniscus to touch the number. You don't do it at the edge because this doesn't count. This is this water surface tension here, okay? And adhesion is between water molecule with other water molecule. All right. Solutes and solvent. We started to learn this in the lab. Water is a solvent. It's the most abundant solvent. It's defined as a substance that does the dissolving. A solute is a substance that is dissolved in the solution. For example, an example of solute is your say sodium chloride, for example. And that's how you make a solution, in that the solute dissolve completely in the solvent. Water is considered universal solvent because it can dissolve a lot of polar molecule. There also, solvent could be non-polar solvent, like oil. It's good to dissolve all the steroid hormone, right? Your estradiols or progesterone, those are all non-polar. And if you want to dissolve that, you have to dissolve it like in peanut butter oil or, other kinds of oil. All right, so hydrophilic means water's loving, and hydrophobic is water feeling. Essentially, hydrophobic is water fearing. All right, amphipathic molecule that has both. Right, substance interaction with water. I'm not going to talk much about that. What happened here? I don't know what's going to happen over there. Okay. What's going on? All right. So the next thing we're going to talk about is this idea of pH. Okay. And think of it as pH is the measure of acidity. And acidity depends on this. All right. When we write the bracket like this, okay, this is the concentration. So it's the concentration of the hydrogen ion, okay, a proton. Okay, so that's what pH is. It stands for potential of hydrogen ion. It's potential of hydrogen ion. Now, it is defined as minus the log of the concentration of the hydrogen ion. Okay. Now, let's say, for example, in water, you have water. Let me go back. Let me stop sharing. Share. All right, so basically, we're going to move that up there. Here's my email address. All right, so what is pH? pH is equals to minus the log of the concentrations of hydrogen ion. Now, if you guys never studied log before, what really means that this log is based on a power of 10. So in other words, what does the number that I need so that it will give me this concentration? For example, if I ask you, what is the log, just in general, log of 100? What is the answer? What is log of 100?
10.
Elsie?
10. 10.
No,
One.
no,
One. Two.
no. Now, why do you get 2? Because I'm asking for you is that what number do I need to raise 10 to get 100? Right? So you say 2
Two.
because
Yeah. Yeah. 10
yeah,
times
10 to the 2
2
is
power.
equals to 100,
Yeah.
right? So again, this is the same thing as say, what is the log of 1 times 10 to the 2? 100 is the same thing as 10 to the 2, right? So what is the log of 1 times 10 to the 2? What's the answer? Elsie?
100.
No.
Wait.
1 times 10 to the 2 is the same thing as 100. The question is, what is the log of that? The answer is 2.
2. Yeah.
Oh,
So,
Okay. Yeah.
right? So in other words, let's do one more time. What is the log of 1 times 10 to the 3? What's the log of 1 times 10 to the 3?
That's 3.
3, right? That's mean I need to raise 10 to third power to give me this concentration, right? Let's do one more time. What is the log of 1 times 10 to the 6?
6.
6.
Good. Beautiful. What is the log of 1 times 10 to the minus 2?
-2.
Negative 2. Good. So negative 2 is the same thing as saying, what is the log of 1 over 100?
-1.
No. 1 to the 100 is the same thing as log of 10 to the minus 2.
Yeah. Second.
So what is the log of 10 to the minus 2? It's minus 2.
-2?
Yes.
Oh, okay.
Okay. Now, here's a question. What is the difference between this one versus this one? You see, this one is 100, right? This is 100. So this right here, it is more than this. This is 1 divided by 100. This is 1. This is 100. Is very, very big, right? All right. Now, how do I clear this? Do you guys have problem? Okay, I got it clear. Do you guys know log yet or no? I don't think that's log is that hard. Let's do one more time. What is the log of 1 times 10 to the minus 7?
-7. -7.
Minus 7, very good. So it turns out that if you look at water molecule, the concentrations of the hydrogen ion in hydrogen ion in water is 1 times 10 to the minus 7. This is, it's 1 to 10 millions of molar. Okay, so basically it has this amount of hydrogen ion. It's small, but it's very important. It's very critical. And that is because, remember, pH is equal to minus the log of the concentration of the hydrogen ion. So if the hydrogen ion's concentration in water is 1 times 10 to the minus 7, right? So what is the pH of water? Technically, the pH of water is minus the log of the concentrations high on 1 times 10 to the minus 7. It's the same thing as minus, it's the same thing as minus the log, oh wait, so that's the same thing as minus 7 or pH of 7, right? Now, what is the difference between 10 to the minus 7 and minus log of, say, 1 times 10 to the minus 6? What is the minus log of 10 to the minus 6 is what would be what? What is the log of 10 to the minus 6?
6.
Minus
And
6.
minus a minus 6 will be 6,
Yeah,
And positive.
16.
right? Will be 6.
Mhm.
So the take-home message is this, okay? pH of 6 has 10 times more hydrogen ion than pH of 7, okay? From here to here is 10 times more, right? Let's do it one more time. What is the minus log of 1 times 10 to the minus 5?
That's 5.
Right. So this would be 5. So from 5 to 6 is how many times more? 10 times.
10 times.
And from 5 to 7 will be how many times more?
20.
Not 10. It's 10 and 10 is 100 times.
10.
And then from 4 to 7, pH of 4 and 7. So even though you say that, oh, the pH of 4 differ from pH of 7 by 3, right? 3 number. But in terms of the hydrogen ion is 1,000 times more, okay? So make sure that you know that. Because every unit in pH is equal to 10 times the concentration, right? Okay, so this is the pH scale. Okay, so you can see here the pH value. The highest concentrations of hydrogen ions is when pH is 0, okay? And the lowest is pH 14. So this is the hydrogen ion concentration, 10 to the minus 14. Remember, pH is defined as minus the log, right? We're saying. So you can say 10 to the minus 14 is equal to minus 14. Minus 14 is 14, okay? So the difference between minus 7 and minus 8 is 10 times, right? Between 7 and 6 is 10 times. 6, of course, has 10 times more acidity than 7. And from going from 4 to 7 is 3, but this is 10 to the minus 7 versus 10 to the minus 3, right? This is 1,000 times more hydrogen ion, right? All right, so keep that in mind. And that is, here are some of the example in the stomach, your hydrochloric acid. The stomach produces a lot of hydrochloric acid. So the pH there is around 2. Lemon juice, of course, is very acidic. Water, pure water is supposed to be 7. Um, Saliva is slightly acidic, whereas here you see sodium hydroxide. It's a base, right? It's a strong base. Has a pH of 14. Bleach has a pH of 12. In general, we call these are very alkaline. Okay. All right. Now, um, typically, an acid will neutralize as a base, and a base will neutralize in an acid. And what is the buffer? Well, a buffer is a substance that neutralizes, well, let's say, a buffer is a substance that is resistant to pH changes. Okay. And one of the best buffer system is the carbonic acid. And it looks, does it have a structure? Okay. So carbonic acid looks like this. Hydrogen. This is carbonic acid. If you put carbonic acid in water, it will give off a hydrogen ion. Okay, like this. See how it gives off a hydrogen ion like this? So we can say, oh, that's an acid, right? So hence the name carbonic acid. An acid that gives off, it's a weak one, as opposed to strong one. Had it been strong one, it will lose this hydrogen ions as well. Okay. Now, this one right here, bicarbonate. Okay, bicarbonate is a base, a weak base, is because it can interact with hydrogen ion and push the reaction goes this way to become carbonic acid, right? And so if you have a buffer, let's say in the lab, you have a solution that's called buffer 7, and you add some acidic acid to it, right? This hydrogen ion, and you will see that this bicarbonate, whatever the solution is in that pH, can add to that hydrogen ion, can react to that hydrogen ion so that the buffer doesn't change. Okay, so it stays at 7. So buffer 7, if you add a little acid, it stays at 7. Buffer 7, if you add a little bit of sodium bicarbonate, a little base, it doesn't change as well. Okay, so that's why it calls an acid. In our body, if you have a lot of lactic acids that give off this hydrogen ion, the lactic acid, or the acid, which is hydrogen ion here, can react with the bicarbonate to push the reaction to become carbonic acid. Okay, and sometimes what you see is that you can develop some alkalosis, right, which is basically not a lot of hydrogen ion, and to balance it out, you just break this bicarbonate. Okay, it becomes this. So that's why the best buffering system in our body is this system here called carbonic acid. And this allows us to maintain our body as the physiological pH of 7.35 and 7.45. Okay, I'm not sure if that's going to be an exam question, but at some point, physiological pH in our body is 7.35 to 7.45. All right, a mixtures is basically a form when you combine two or more substance together. It's not important. In the relations of the lab, a suspension is where particles are not dissolved, but the rather even though you add the particle in water, they don't dissolve, they just suspend it, right? So, and oftentimes a suspension will be cloudy, opaque, and if you shine the light, it doesn't go through. And the suspension, and that is the particle, will settle down. And a good example of suspension in our body is the blood. If you put it, take out the blood, leave it room temperature, it will comes down. It will settle down. A colloid is a special kinds of suspension, but the particles do not settle down. An example of that is your blood plasma that has your proteins in there and antibodies, but it doesn't comes down. Okay, it remains suspended. Okay, a solution is defined as a mixture in which the solute dissolves completely in the solvent. And typically, if you have 10% 10% sucrose solution, that means you measure out 10 grams of sucrose and dissolve it in total 100 ml. Okay, you do not take 1 ml of water and put in 1 gram. If you do that, you displaces the water. It will be more than 100. So typically what you do is you just measure 80 ml of water, add 10% of glucose, dissolve it, and then add the remaining water so it can reach 100. So 10% glucose solution is 10 gram, okay, of glucose, for example, 10 gram of glucose in a maximum of 100 ml of water. Okay. That's what percentage means. Percent is based on 100. If it's 20% glucose, you will measure out 20 grams of glucose and to dissolve it in maximum 100 ml. Right? So you don't want to start with 100 ml because you put in 20 grams, it will displace that volumes of water. So you wanted to measure out like 80 ml of water, throw in your 20 grams of glucose, and even though it's displaced a little bit, it's okay. You can add the rest of the water, so its total is 100. And emotions is basically when you have a lot of these fat droplet, nonpolar molecule that breaks into small chunk, if you will, and that's known as the emotion. And emulsifier, the thing that could basically breaks down this emotion, it would be like the content that you see that is released into the small intestine is known as bile. Okay. All right, so here's to show you an example of a blood. Your blood has your plasma, you have your, if you take the blood out, right, and if you spin the blood, you'll see that, and this is what something we do in the lab. In 302, you will separate the blood into 3 fractions. The plasma part, which is constitute about 55%. This packed cell volume, or your red blood cells, about 45%. And this middle region here is known as the Buffy coat, which has your white blood cell, also known as your leukocyte. But in that, it has your platelets as well. This whole blood right here is considered a suspension, because if you leave this at room temperature, it will settle down. And to speed up the separation, you can put this tube in a centrifuge and subject to centrifugal force. So then this was then separates it. Red blood cell is heavy because it has ions in there. It will settle down first. The plasma has your albumin, fibrinogen, and other protein in here as well, but those particles does not settle down. right? So it's a special kinds of suspension is known as colloid, right? An example of colloid would be, say, gelatin, for example, that has some protein in there, or particle that does not settle, right? An emulsion, and that if you mix up with oil and water, this is emulsifier emulsion, okay, in which these polar molecule, which is water, and non-polar forms an emulsion. And ultimately, what you see is all of the yellow particle will merge together to becomes the oil and then the water. This is your typical, you know, um, your salad dressing, oil and vinegar. And the reason why this has occurred, because oil is hydrophobic. It doesn't not like to interact with water, right? And water is hydrophilic. But if you have all the oil droplet, right, merged together, right, all this area here, there's no water, right? The only interaction with waters will be here, right? Whereas here, there's water interact with many of them, right? Potentially interacting with them, or these oil droplets surrounded water, and it doesn't want it to do that. So what happened? It's going to all forms together into compact region of oil to minimize the interactions of water. All right, so let's take a 5-minute break, and then we'll talking about the macromolecule and what are these macromolecule are made out of, and that will be the your exam 3 will be up to these macromolecule. Okay, any question? I'm going to stop here.